Morning students, today we are going to discuss the type of covalent bond. In our previous class we have started the valence bond theory and we have discussed that how it explains the formation of the hydrogen molecule. It could not the existence of helium as a diatomic molecule is not possible because according to the VBT, the when a chemical bond or a covalent bond is formed, it is formed by the overlapping of the atomic orbitals, half-filled atomic orbitals. But in case of helium, it has got the completely filled atomic orbital, that is 1s2. So when the two helium atoms atomic orbital, the valence shell atomic orbital will approach, they already have two electrons in them and hence the overlapping is not possible, right? So I think this is clear that why helium molecule doesn't exist on the basis of VBT, because the valence shell atomic orbital of helium contains fully filled atomic orbital. Right? Now we will just move to the next topic, that is the type of covalent bond. Now students, depending upon the type of overlapping, so depending upon the type of overlapping, the covalent bond is of two types. First is the sigma bond and second is the pi bond. So we are going to discuss the formation of the sigma bond and its type at first, right? So we will begin with the first type. So the covalent bond, it is of two types. One is the sigma bond and second is the pi bond, and this classification is based on depending upon the type of or depending upon the nature of overlapping. Right? So we will start with the first, that is the sigma bond. Now student, the sigma bond, when the two atoms comes closer, right, the overlapping of their atomic orbitals, which is along the internuclear axis, right, this can be known as the head-to-head or end-to-end overlapping, result in the sigma bond. Or we can say the sigma bond, it is a bond formed by the overlapping of atomic orbitals along the internuclear axis, right? This, or you can say that it is the end-to-end or head-to-head overlapping, right? Now students, here we'll start, let us take an example here for the formation of hydrogen molecule. So here we have hydrogen, the valence shell atomic orbital is, this is 1s, right? This is the internuclear axis, this is the another, right? So there will be head-to-head overlapping, and this is head-to-head overlapping. It is taking place along the internuclear axis, right? And the molecular orbital. Now, student, these are the atomic orbitals, right? So when, and this is the overlapping region, that is the penetrating region of the two atomic orbitals, right? And the molecular orbital which will be formed In case of, this is the molecular orbital, right, which will be formed here. And student, here the electron cloud, right, the electron cloud will be, right, we can symmetrically distributed along the internuclear axis, right. Here this is s orbital, this is another s orbital, right, and this type of overlapping is known as the ss overlapping, right. So I think this is clear that what is a sigma bond. The sigma bond is formed by the head to head overlapping of the atomic orbitals, or end to end overlapping of the atomic orbitals along the internuclear axis, and the electron cloud which will be outcome, okay, of this overlap, right, is going to be distributed evenly along the internuclear axis. Now students, we are going to discuss the type of overlapping, that how many types of overlapping, sigma overlapping is there. And student, it is going to depend upon, right students, it will depend upon the orbitals which are involved in the overlapping, right, and how many, whether it is two s orbitals are involved, right, or one s and one p involved, or the both other p orbitals. So next is the types of sigma bond. So the first type we have discussed, that is the ss overlapping, right. So the first type was ss overlapping. Now students, second type is the S and P overlapping. Now let us assume the formation of student HF molecule, right. So here we have H, outermost or valence shell orbital is 1s, and the fluorine, right, it will have, you know that the fluorine atomic number is 9, and you can write down its configuration. So it will be here how much student, 2px, I am writing the valence shell 2py and 2pz, right, it is 27, right. So the second shell, 7 electron will be distributed, 1s2, 2s2, 4 and 2p5, right. So here 5 electrons means it will be 1, 2, 3, 4 and 5, that is 2, 2 and 1. Hope so this is clear to you. Here I am writing the outermost shell configuration, 2s2, let me write completely here, this is there, this is the valence shell configuration, this is the configuration of fluorine, 1s2, 2s2, 2p, 2p5, right. So we will consider here the outermost shell, or here valence to second shell it is, and which has got the half-filled atomic orbital, that is 2pz, right. So we are considering here the 2pz orbital which has got the a p orbital which has got the 1 electron available with it, this one, right. This is the internuclear axis, similarly this is the internuclear axis. So here along the internuclear axis the bond formation will take place in this way, right. This is the sp overlap which is taking place, right. So here 1s and this is 2p, so they are going to overlap and form the we can say the molecular orbital, right, where the electron density will be evenly distributed right along the internuclear axis, right. As a result, what will be the molecular orbital which will be formed? This is the molecular orbital which is going to be, I am representing molecular orbital with MO, students. Here it is, M stands for the molecular orbital, M so is molecular, O stands for the orbital. So students, this is the HF molecule overlapping which is taking place, and it is known as the sp overlapping, because here we have got one orbital of s, right, another orbital is p, so it is sp overlapping. Now the third type, student, is the pp overlapping. Now the next type that is here is the pp overlapping. Right, so let us consider here the example of fluorine molecule F2. Right, F2 formation, we are taking fluorine molecule formation. Now as we know that the p subshell will have one atomic orbital will have half filled configuration, so let it be this, right. So this is the 2p of fluorine. In the similar way we will have another 2p of fluorine. Right, now one thing I want to mention here, that the overlapping will be always of the same sign, right. This is plus, this will be plus, right. We are going to discuss later it again. So it is plus and plus, or if it will be minus, it will be also minus, right. So overlapping will take place. This is the pp overlapping which is taking place here. So it is 2p and 2p atomic orbitals, they are just half filled and of the same sign, they are going to overlap and form the pp overlapping, right. And the outcome is going to be this is the molecular orbital which will be formed by the pp overlapping, right student. So these are the different types of sigma bond which will be formed, right, by the overlapping of ss orbital, pp orbital, s and p orbital, and pp orbital. So on the basis of that we get ss overlapping, pp overlapping, and sp overlapping along the internuclear axis, right. These all overlapping are taking place along the internuclear axis. Hope so this is clear. This we have discussed the type of sigma bond, right. And again I am repeating, what is sigma bond? The sigma bond is the overlapping, a bond which is formed by the overlapping of the atomic orbitals along the internuclear axis, right, which is head to head or end to end overlapping, right students. And since in this way the penetration of the orbitals into one another is of greater extent, so hence the extent of overlapping is maximum in the sigma bond, right. Now in the next we are going to discuss the pi bond. Now we will discuss the pi bond formation, right. So how is the pi bond formed? So for that, whenever the two atomic orbitals, right, undergoes the lateral overlap, or the we can say sideways overlap, right, perpendicular to the internuclear axis, a pi bond is formed. So the second type is the pi bond. So when the lateral or the sideways overlapping perpendicular to the internuclear axis takes place, pi bond is formed. right? So it is whenever there is a sideways or lateral overlapping taking place, and that is not along but is perpendicular at a right angle to the internuclear axis, it will be known as a pi bond, right? Now let us take an example here, right? If this is the p orbital and this is the another p orbital, right? This is along the positive axis, this is along the negative axis, this is plus slope, this is plus slope, this is negative low, this is negative low. If the overlapping is taking place in this way, what will happen, right? So this is, you can see that it is not along the internuclear but it is perpendicular to the internuclear axis, and it is a sideways overlapping. It is not, student, head to head overlap in this way. The overlap will take place, right? So as a result, this is along the internuclear axis, and the electron cloud, you can see, will be up and below the plane, right? So this is the pi bond formation, right, where there is, we can say, the sidewise overlapping take place, right, and a pi bond is being formed, right, students? So in the similar way, now we will try to, okay, now this is the pi bond. So here the pi bond formation is taking place, right? And if it is sigma bond, what will happen? How the overlapping will take place? It is in this way, right? Hope so this is clear, that the difference between the overlapping, what is head to head overlapping and what is the sideways overlapping or the lateral overlapping. Now students, we will try to see the pi bond formation along with the sigma bond, right, in the oxygen molecule. Right, students? So here we can see that okay, one more thing is there. A pi bond cannot be formed alone, right? First the sigma bond will be formed and then the pi bond forms. If it is required, the pi bond will be formed. Otherwise, the basic bond, fundamental bond, is the sigma bond. The basic covalent bond or the fundamental covalent bond that is formed first is the sigma bond, right? Now let us see the oxygen molecule. For that, we need two oxygen atoms, and the configuration, atomic number is z equals to 8. So its configuration will be 1s2, 2s2, and it will be 2p4, right? So it is 1, 2, 3 and 4. So we are getting it in this way, right? So this is the configuration of the we can say of the oxygen atom. It is 1s2, 2s2, 2p4, right? So here, the valence shell, you can is 2px, 2py and 2pz. 2s2 is filled up, 2px is filled up, only 2py and 2pz are there. So let's start here, that if this is the oxygen atom here, right, since here the only the p or p shell will be involved in the sigma bond formation, right? So we are going to show it in this way, that this is for one oxygen atom and this is the, it's another atomic orbital, the p orbitals available, right? These are the two p orbitals on oxygen, of oxygen. Similarly, the another will be also there, another oxygen atom. This is for the another oxygen atom, right? Now when the overlapping will take place, now you can see that this and this is the pi bond overlapping which will take place. Before that, the sigma bond will take place, formation will take place. So student, here it will be in this way, right? And the pi bond overlapping, we are going to show it in this way. So that means this is the sigma bond which is formed, and this is the pi bond which has been formed. So in the oxygen molecule, students, two oxygen atoms, they are held by, this is the sigma bond, right? And we have one pi bond, right? Now for the pi bond formation, the p orbital are going to overlap from the two ends. Then only a one pi bond is going to be formed, right? So here, student, we are just so the this is the along the internuclear axis. This is perpendicular to internuclear axis. These two are the 2p orbitals which are half filled. Hope so this will be visible to you. The 2p orbitals in both the case, they are half filled, right? That is in both the oxygen atom. I think this is not visible, but the orbitals which I have written here, the 2p orbitals of both oxygen atom, they are half filled orbital. Right, students, these both orbitals of both oxygen atom, the 2p orbitals involved here, both are half filled. Right, so I think this is clear that the pi bond will be formed by the sideways overlapping. Right, again here is also there the atomic orbitals will be half filled, right, and the overlap will take place between the same sign or the same lobes, right? If it is plus, this will be also plus. The positive overlapping will take place, right, students? And sigma bond is formed first, and then the pi bond formation takes place, right? So pi bond cannot be formed alone, it will be formed always along with the sigma bond, right? So here in the oxygen molecule, it is clear that we have got one sigma bond and one pi bond, right, student? Now, students, we are going to discuss the formation of the nitrogen molecule, right? So here the nitrogen, you know, atomic number is 7. Also on each nitrogen atom, the number of the electrons available for the bond formation, so it's 5 and this is 6, 7. So you can see that we have got 2p3, the half-filled configuration. That means in each orbital we have got each 2p orbital have got one electron each. So here in the diagram, right, I have shown this is the axis, right, and along the axis we have got the p orbitals here, right? This is for the one nitrogen atom. Similarly, for the another nitrogen atom also we can draw, right? So these are the atomic orbitals, p orbitals of the along the x-axis, y-axis and z-axis, right? So here you can see there will be head-to-head overlapping. So here the sigma bond will be formed, whereas in the rest two types of atomic orbitals there will be pi bond formation, right? So here the pi bond which is going to be formed here will be in this way. So first we will show the sigma bond which is being formed. So this is the sigma bond between the two nitrogen atom, right? So here in this way, this will be the first pi bond which will be formed, right? The another pi bond which will be formed, it is this one. So this is the pi bond which is formed, right? So you will see that, so here the lobes along the axis, right, is going to overlap. It will be not so that y-axis is overlapping with the z-axis. It will be x to x or z to z, right, students? So this is the pi bond which is formed here, and this is a sigma bond which is formed. So in the nitrogen molecule, student, this is the nitrogen, two nitrogen atom. They will be held by first a sigma bond. This is the basic bond, and then the pi bond formation will take place, right, students? So here we have one sigma and two pi bonds involved, right? So whenever it is a double bond, we will have one sigma and there will be one pi bond. And when it is a triple bond, then we will have one sigma and two pi bonds formed. Now student, the next is if we compare the strength of the sigma and the pi bond, right? So on comparing, we will discuss now two topics regarding the sigma and pi bond. The first is that what is the strength or the strength of sigma bond and the strength of pi bond. Now you have seen here that where is the extent of overlapping maximum, or where the two atomic orbitals can penetrate to greater extent. Is it through the head to head or through the sideways? So you can see here that the sideways will always have a restriction, right? So if we take this one, this overlapping, this is the pi bond overlapping, the sideways overlapping, it will always have a restriction to it. Whereas the sigma bond doesn't have restriction. So that means the extent of overlapping is going to be maximum on the sigma bond formation. So hence, since the extent of overlapping is maximum in sigma bond, right? Therefore, the strength of sigma bond is greater than the strength of the pi bond. This is the first point. Now the second is the symmetry of the sigma bond and the pi bond, right? So if you see that when we have discussed the formation of sigma bond, right, so we discussed that whenever the atomic orbitals, the valential atomic orbitals which are half filled, they overlap with one another, the molecular orbital which is formed will have the electron cloud distributed evenly along the internuclear axis. So there is a symmetrical distribution of the electron cloud along the internuclear axis, whereas in the pi bond, right, there it is, we can say the electron cloud is distributed up and below the internuclear axis. So it is not that much symmetrical distribution as it is found in the sigma bond, right? So students, you will just get it noted down. First is the strength of the bond, which bond is more stronger and why is it so, and second is the symmetry of the bond which has been formed, or the symmetry of the electron cloud distribution which is obtained through sigma bond and the pi bond, right students? So please get this thing noted down in your notebook.